Okay, well, today's the big day, the day of the third and final milestone of the project. So, I'm hoping that it's mostly done or you're well along the way, but are there any questions that we can answer before we, yeah. Yes, that's a good question. And so the question is, with the abstract argument one, you need the integer value. And actually, I modified I think it was the assignment 19. I put a little note up there that recommended that you write a getter called getInt value. Got a question? Yeah. Oh, that's a good question. Yeah, that's a good question. So here's the question. The question is, when you have a branch instruction, because it has a default addressing mode and it's okay for the user to leave off the addressing mode, how should you handle that? Should you hard code that, or should you maybe use a table lookup or something like that? And that is a really good question. The answer is, it's up to you. Because look, in fact, this is a good software design issue that comes up all the time. And do you remember how when we first learned how to implement finite state machines, we had table lookup and we had direct code technique. That is an issue that comes up in software engineering all the time, because frequently you can do it either way, and the choice is up to you. That is a design decision in software engineering. And basically what you do is you just have to see, well, how difficult or how much complexity would there be in doing it one way, and versus how much complexity would be to do it another way. Sometimes it's good to do it one way. Sometimes it's good to do it another. Sometimes it's better to do it the other way. So you just have to, you just have to assess, how you want to do it. Yeah. But this is one of many side benefits that we get, that we learn by doing a big project like this. Yeah, these software engineering issues. Oh yeah. So the question is, how do you do the code generation for the branch instructions? And that's right. And so here again, you can hard code the case for the branch instructions, because that's different from the other ones. Or you could do it. I've had students do a branch instruction addressing mode with an enum that has an I and an X. Yeah, okay. And then the ordinal value of I is, but whatever floats your boat. Yeah, no, those are decisions that you can make. Okay. Either way is fine. Certain things I insist you do it one way, but that's up to you. Yeah, these are good questions. Any more? Any other questions? Okay, so yeah, a lot of you guys have come along quite well. This is, I think, this is a good experience for us. Now, I think what let's do now is, before we go on to a new addressing mode, let's go back and review what we did before. And I think I'd like to show you in a little demo what we did last time. Last time we saw this slide that defines indexed addressing. And we see with indexed addressing, what happens is the operand is calculated by taking the operand specifier plus x, and then that is the address of where the operand is. And we had a program that used indexed addressing where the array was a global array. Do you remember that? That was for global variables. And then here was the recipe for global arrays. And we did a little translation of a program that did global arrays. And then we did the same, and here was the memory model in figure 6.35. This was the memory model. And you notice that the array vector is at a fixed location in memory, and J is at a fixed location in memory, and so it's not on the runtime stack. And then we translated a program that did that. And then the next addressing mode that we looked at was stack indexed addressing. And here what happens is the operand is calculated by taking the stack pointer plus the operand specifier plus the content of the index register. And so this was, because the stack pointer is involved here, this is when the array is what? Not global, but local on the runtime stack. And we did a little calculation to show, and then that, the SP plus operand specifier plus x, that's the address in memory of where the operand is. And the assembly language 5 letters for that are SX. And then we took a look and we saw that, so this was the recipe for local arrays. you allocate the number of bytes with sub SP total, and you use stack indexed addressing to access the element of an array, of a local array. So what I'd like to do now is just to give a little demo. So let's do a demo. Okay, so here in figure 6.34 is the C program. And here we have int vector4 and int j, and these are global. And this is the program that we translated, and here's the translation for it into PEP9 assembly language. So we'll copy this to source, and we will build it. And now watch this. So here the input is 60, 70, 80, 90. And let's start debugging. Now watch what happens when we start debugging. Boom. So look, because we did this, because we had a vector and dot block and 8, and we have global variable. Now what is this hashtag 2D4A? How do you say that? 2-byte decimal, 4-cell array. So because we did that, we specified that, then this vector comes out in the debugger like this, vector 0, vector 1, vector 2, vector 3. And then j is a global variable, 2-byte decimal, and so j is here. And so there's nothing on the runtime stack. These are global. Now let's single step through this and watch what happens. So we'll single step through here. So we branch to main, all right? And main says load word index register. So we load word index register, and so 0, so 0 is in the index register. And then we store that to j, so now so j gets 0 there. And then we do our if state, the test for the for statement, but we're not going to branch out. And so we do an ASLX. Well, this is kind of uninteresting because if you double 0, you get 0. All right, and then we decimal input into vector sub 0. And so there the 60 went into vector sub 0. Let's go down to 2. All right, so here's j as 1. Deci into 1, add x. Oh, so now here so now this is load word j direct. So j, and then add index register 1, so that j is incremented to 2 here, and then we store this to j. So look, so j is going to get 2. So here's j is 2. Now we branch back to here. Now check this out, you guys. So here we compare, and we're not going to branch. Now watch this. We are about to do ASLX. So this is 2. So if we do ASLX, this 2 will become what? 4 is correct. Are you with me? And now we're going to decimal input. But now look, what is stack index do? What does it do? It takes what plus what? What is the operand specifier here? What is the value of the operand specifier with this instruction? Somebody tell me. What?
Pointer plus vector plus x.
No. No. What is the operand incorrect. Sorry. What is the operand specifier for this instruction right here? This is the deci, vector, comma, x. What is the operand specifier?
Vector.
Vector is correct. That's the operand specifier because that's, and what is the value of the operand specifier? 0, 0, 0, 3. Are you with me? Is everybody clear on that? The operand specifier is 0, 0, 0. Now what is the operand specifier plus x? So the operand specifier is 0, 0, 0, 3. And what is the index register? 4. So what is the operand specifier, 0, 0, 0, 3, plus this 4? 0, 0, 0, 7. And what is at 0, 0, 0, 7? 0, 0, 7 is what? Vector sub what? Sub 2. So when we do this, what we deci into what? Sub 2. Now did everybody see how that worked? Are you with me? Here, let's pause here and go back to. Let's pause here and go back to what the operand. It's here. The operand specifier. All right, was 3. The index register, the content index register was 4. It was 2 doubled. 3 plus 4 is 7. Mem sub 7 is where that is. Does everybody see that? Okay, so that's all right. Is everybody clear on that? The operand specifier is that part of the instruction that comes after the instruction specifier. That's that 2-byte field. And in this case, the operand specifier is in this DESI, the operand specifier is this vector, and its value is 0003. Are we good?
I didn't realize they were not on the stack right now.
Oh, right. Yeah. Okay, and now we can keep single stepping through this. And here it prints out, it does the other loop, and it comes out, boom, 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 boom. Are we good? Does everybody see how that works? Now here, let's demo the other one. Let's demo, let's demo 636. Copy this to source. Okay, we'll come up here and clear memory. All right, and now now this is the one, notice here that vector and J are going to be, we're going to have sub-SP, so they're going to be on the runtime stack. So let's build this, and let's start debugging this one. Okay, and so now the first thing we're going to do is branch to main. Now watch this, we're going to branch to main. And now the first statement in main was what? Sub-SP what? 10 immediate. And what are we pushing? Vector and J. So we'll push vector first, and then we'll push J. So here we'll single step through here, and look, is that slick? Boom. Vector 0, vector 1, vector 2, vector 3, and J is here. Is everybody clear?
So the computer...
Yes. The hashtag is what allows us to see all of this stuff in this symbolic debugger. Yeah, this PEP9 desktop app requires those trace tags so that we can view it visually like this.
So if that were to be, like, our...
No,
would not be able to do this.
Hold on. This equate to, why does vector equate to 2? That's because when the value of the stack pointer is FB85, vector, it's the offset, so it's 2 bytes down. It starts here. That's what the 2 is. You can run these programs without these trace tags.
And then if you...
But then the symbolic debugger is disabled and it won't show.
Yeah.
So look, so now let's run through this a few times, and let's get it to where let's get it to where J is 2 again. Okay, so we'll just single step down through here. So here J is 0, J is 1. All right, and now we just added one. We did load word index register J, and J was 1, and we added 1 to the index register, and that made it 2. And now we're going to store word index register J stack relative addressing. So what's going to happen here? Boom, J is going to get 2. Now is everybody clear on that? And then we branch back to the for loop. We're going to do the test, and we're still going to be in the loop. So we will not branch if greater than or equal to, because J is not greater than or equal to 4. And now look, you guys, what is ASLX going to do with this value in the index register? It's going to do what? Double it. It's going to multiply it times 2. So boom, the index register is going to be 4. Now we're DESI into what location? DESI vector, but what addressing mode? Stack indexed. Now how does stack indexed work? You take the what? The value of the stack pointer. Can you tell what the value of the stack pointer? Oh, here, look. Here's the stack pointer. What is the value of the stack pointer? 0x what? What does it say there? FB85. See? FB85. The stack pointer is pointing right there to the top of the stack. Okay, so it takes the stack pointer, FB85, plus what? The what? Plus the what? Operand specifier. What's the operand specifier? 0002, because that's what vector is in this case, 0002. Now what is FB85 plus 0002? FB87. But then what do we do with that FB87? We have to add what? X, but what's in the index register? 4. So what is 7 plus 4? 7, 8, 9, A, B, right? So it's what? FB8B. So when we DESI into there, where do we go? Boom, into vector sub 2. Now, does everybody see how that worked? You can see it all visually right here. You can see the content of the stack pointer. You can see everything. This is really, you should do that. You should study these Just understand how this works, yeah.
So if this were an array of characters, then you wouldn't need the ASLX.
That is a very good point. If this were an array of characters and each character occupied 1 byte, that is absolutely correct. You would not need to do the ASLX. And if you were in a computer where the integers were 4 bytes, you'd have to do what? ASLX, ASLX.
Yeah, shoot it twice.
You see what I mean? Because you multiply by 4.
Yeah.
Yeah, that is a very good observation. Does everybody see what you have to do? You have to adjust what the value is. And this is way common. This happens. This is just way common in computer systems and how to deal with array, how to access arrays. All CPUs have array. You have the capability to access elements in an array in the hardware like this. Okay, and then so here let's just do this out, and here the numbers are coming out in reverse order with the index and okay. So there we have it. So that's our demo. Okay, so that's the demo. Now, there's only 2 addressing modes that we have yet to learn. One of them is indirect addressing, and another one is the most complicated of all. It is this stack deferred indexed addressing. So now what this does is this does indexed addressing, but it does a little deferral. It does a stack deferred before it does it. Now let me just say that this addressing mode is what is needed when you pass an array as a parameter. Are you with me? So if you have an array as a parameter, then what happens is what you pass is you pass the address of the first byte of the array. You pass the address of the first byte of the array, and in C languages, in C and C++, arrays are always passed by default. They are always passed by value. In other words, the address is always what's pushed up onto the runtime stack when you pass an array as value. And here's the definition. What happens is you take the stack pointer plus the operand specifier. So imagine, you can kind of imagine. Here you have the runtime stack, right? And on the runtime stack, the array, the address of the array is going to be down here somewhere on the runtime stack. So you take the stack pointer plus the operand specifier. That's going to give you the cell in the array that's the address of where the array is down below. Okay? And so mem sub that is the array somewhere else, either global or local, down here. And then from that, you have to add x to that and take the mem of that, and that's where the, can you follow that? I mean, it's one more level. But this is the way it is, stack deferred index addressing. Now here's the thing, you guys. Here's the recipe for passing a local array as a parameter. I'll just tell you right off the bat, you don't need to know this. Okay, I don't have a homework assignment for you to do this, and you don't need to know it for the exam. But this is just, we just don't have time to do all infinite detail here. So we're going to skip this one. But I just want to show you the way it would work. And on figure 6.39, I just want to take a minute to show you this. So here in figure 6.39, in part B is after calling a function called getVect, which is getVector. And you can see here, let's take a look at the C program. Here, let's take a look at figure 6.38. There is a main program, and there is a vector that has 8 cells in it, and then num items is another local variable. So vector is a local variable, and num items is a local variable. And we have this function called getVect. And what it passes the vector as a parameter under the runtime stack, and then getVect, accesses v. So that's the setup. And so if we come here to figure 6.39b, what we see is that, now look, what we see is that SP is pointing to that very top cell, FB75, and where is v, the formal parameter v? That is how far down from the stack pointer? Can you see it there? It's how many bytes down? It's 6 bytes down, right? Okay, so the stack, so SP, so 6 bytes down is the V. And then what is in V? What is the content of that V? That's what? FB what? 7F. But now, what is at FB7F? Vector sub what? Vector sub 0. So the question is, how do you get to vector sub 2? So what you have to do is you have to take the content of the stack pointer, which is FB75, add the what? The operand specifier, which is V, which is 6. Are you with me on that? And then it's the mem of that is what? FB7F. And then from that FB7F, you add the index register, which has been done an ASL on, and boom, you get down to sub 2 below. Yeah, I think you can, sounds like some of you are following this good. Very good. So anyway, that's just another level of complication, but anyway. And you're not responsible for that one. But now, okay, so here are the 3 new addressing modes that, and comparing X with SX with SFX. It's kind of weird, you know, because this plus X is not inside here. It's because you have to do SB plus operand specifier to get down there, and then you got to add the X, boom, after you get down there, you know. So you can see. But on the other hand, this SFX, it comes into play when we deal with linked lists. You know, this is going to come into play. We're going to use SF. We're going to use this addressing mode in a different context. All right. Now, this next one is really cool. All right. So buckle up. I think you're going to like this one. Now, you guys know, do you remember when we first started all of this stuff and we first had symbols and stuff? And one of the very first things we did was how an if statement works. And we had those conditional branches. Remember that? And then we did how loops worked. And we'd use the conditional branches to do loops and stuff. Have you ever wondered now about the C switch statement? Have you ever wondered how the C switch statement would work? Now this is really cool, and this comes up in computer systems a lot under the hood. Because what do you do with a switch statement? You say switch what? Parentheses, and you have what? Some variable, yeah, some variable, or it's a variable usually, right? Like an integer variable or an enum.
Yeah, typically like something equals something.
No. It's usually switch.
Switch on a specific variable.
Yeah, switch on a specific variable. And then what do you have? What do you have down below? You have cases. You have cases. Are you with me? Now here's the thing, you guys. This switch statement with cases, it's not like if, else if, else if, else if, else if, else if, where you have to test each one, else if, else if. It's not that. The way the switch statement works is it takes a look at that value of what it is, and it goes boom directly to that case. It does not have to test all the intermediate cases in between. It goes directly to that case. Are you with me? Does everybody see what goes on with the switch statement? It goes directly. Now the question is, how can it do that directly without testing each one before it? How can it, you know, how does it do that? How does it do that? Here's what's really clever. It can do that without having to do all those intermediate tests by using a branch instruction with guess what addressing mode? No. What are the 2 addressing modes that are possible for the branch instructions? You guys should know this one now. Indexed and what? Sorry, immediate and what? Indexed. Now, what do we normally use indexed addressing for? What? Arrays. We normally use indexed addressing for arrays. So what are we going to set up? An array of what? An array of addresses. We are going to set up a little internal array of addresses, and those addresses, what will each one of those addresses be? Each one of those addresses will be the what? The address of each what? Case. Ah, this is so good. You guys are with me.
So is that why the operand was an address of an address?
Well, No, the address of an address, that's different.
Okay.
That's going to be indirect addressing.
Okay.
Yeah. So, does everybody see the concept? The concept is what the compiler does is it sets up its own little internal array of addresses. And what these are called, these have a name. These are called jump tables. And what a jump table is an internal array of addresses. That's what a jump table is. It's an internal array of addresses. Now, in order for us to set up this internal array of addresses in order to do the switch statement, we need a new dot command. And what do you suppose that dot command is called? Dot what? ADDRSS. All right? And look, check this out. How does the dot address dot command work? Every dot address command must be followed by a what? By a symbol. So that's the requirement of that dot command. It must be followed by the symbol. And what code gets generated? The code generated by dot address is the what? The value of the what? Of the symbol. But what is the value of a symbol? The value of a symbol we've always known from the very beginning, from the very get-go when we first did symbols. We always learned what? The value of a symbol is a what? Is the address of where this code is placed. Is everybody, now do you see how all this is connected? Oh, this is just beautiful.
Why is it even necessary to have this command, though?
Because in order to set up this internal array of addresses, in order to set up this internal table, because we need the address of this, we need the address of the first case, the address of the next case, the address of the next case, the address of the next case, and so this dot address dot command will enable us to set up the entries in the jump table. And then when we generate the code, we'll do a branch with indexed addressing, and the index will go to that one in the that one in the jump table, and boom.
I just feel like the symbol already is the address.
I know, but it's not in a table. But we need to collect them all in an array of addresses so that we can indexed by. Do you see what I'm saying? Yeah, you'll see. It'll be really slick. Okay. So now here's how the switch statement works. This is way cool. So here's what you do. And by the way, this is what the compiler does. Because what we can do can be automated by the compiler, right? So here what we do is we set up a jump table with .addrss. And you can put that right in the code because we're going to branch, you can put that right in the middle of the code and it won't be executed because we're going to branch around it, right in the code. So you set up a jump table with the .addrss. And you'll have one .addrss, one dot address for each case that's in the switch statement. All right. And then we'll use load word index register to load the index register with the switch value. All right. And then we will execute ASLX once, because how big is an address? 2 bytes. So in a computer that had 4-byte addresses, if an address was 4 bytes, we'd have to do ASL twice, right? Are you with me? And then we execute what? Branch with what? Indexed addressing. And what that branch, you'll see, there's a few more, we'll see a few little more details we'll have to know, we'll have to see how to do the translation, but a few more, and then it'll happen. Okay? All right, so now here's going to be figure 6.40. Now let's translate this figure 6.40. All right, int main, int guess, printf, pick a number, 0.3, scanf, guess. Now what does it say? Switch what? Guess. And case 0 is printf not close, break. Case 1 is printf close, break. Case 2 is printf blah, case 3 blah blah blah, and returns. Is everybody clear on that? How it does it? Okay, so let's see. Who wants to go first? Okay, so branch to main, and now do we have local variables? Yes or no?
Yes.
Yes, and so what do we have? guess. Oh, so what's our memory model? Guess. And here, it's very simple. The stack pointer is here. So what does guess evaluate to? Or sorry, what does guess equate to, rather?
0.
Yeah, so here we have guess dot equate 0, and this is a what? Local variable, stack to D, and then here is main. You want to go next? Oh, okay, you can go next. That's all right. Okay. Yeah, sub SP, how much?
2.
Sub SP to addressing?
5.
Immediate is correct.
Push.
And this is push,
Yes.
hashtag guess. Right. Next, stro is good. There's going to be 4 messages, right? So let's call it message 0 for the case, to match the case. Message 0, direct. Okay. And now, next, do you know what would happen next? Because how do we do scanf? Yes, deci is correct. Deci into where? Into guess and stack. Relative addressing is correct. Okay, so far so good? Right? Now what we're going to do is we're going to branch. Now we're going to use indexed addressing, right? We're going to use indexed addressing. So to use indexed addressing, what do we have to do first? We're going to postpone, we're going to put the jump table down here in a minute. So unfortunately, you can't see what the jump table is yet because we're going to branch around it later. But what do we have to, but the next executable statement has to be what? What do you think we have to get into the index register? The value of what? Guess. So how do you get the value of guess into the index register?
Word index.
Load word index register what? Guess. Addressing mode? Actually, yeah, it's a local variable, so S. Right? And now we'll see exactly this is going to work in a minute. But how do you switch to the case? How do you switch to the case? What do you think? Oh wait, we have to do one more thing to the index register. Yeah, ASL. Arithmetic shift left index register because it's 2. And now how do we get to the? Yeah. Oh yeah. This is going to be. This is kind of hard to do from scratch here. But here, let's postpone this for a minute. This is going to be a branch. A branch to somewhere using index addressing. And what's going to happen here is down here what we're going to do is this is where we're going to put the array of addresses. And this array of addresses is going to be what? Guess JT. So this is going to be called guess jump table. All right? And let's worry about this one later. So this is going to be our guess jump table. Now how will we set up this guess jump table? With what? Yeah, this is going to be .addrss what? Now what has to come here? A what? Every dot address has to have a what? What did it say? It had to have a symbol. So what will be the symbol? I don't remember what I called it. Here it is. Yeah, case 0. So this would be address of what? We'll call it case 0. This is a symbol that's going to happen later on. And then the next one is what? Address case 1. And then the next one is what? Obviously. These aren't hard questions, are they? Yeah, one more. Case 3. And then what's going to happen is here, at this point right here, here's going to be case 0. Are you with me? And then somewhere down here below is going to be case 1, case 1, and then down here below is going to be a case 2. You see what I'm saying? CASE, case 2. You see? This code is going to be where the executables for those cases are. Are you with me? Okay? And so now here's the thing. What do we branch to now? With this setup, what do we branch to? What do you think we branch to? Guess JT, we branch to guess JT using what addressing mode? Indexed. Indexed. Are you with me? Because what will that do? That will put the, how does indexed addressing work? Do you remember how indexed addressing works?
Does it add on the X to whatever you...
It adds the operand specifier to the what? To the index register, and it takes and it's mem. It's that in mem. It's the mem of that. So what it does is it takes. Yeah. So here's the complete code. Let's take a look at the complete code. Here in Figure 6.40. So guess equates to 0. We sub SP2 immediate to push guess. We throw our first message. I call it message in this listing here. We decimal input into guess using stack relative addressing. We load word X, ASLX, branch to guess JT using index addressing. Now look. Now let's take a look. Do you see down here in the listing? Do you see on line 001B? That is the first executable statement of case 0, right? Now what is the value of the symbol case 0? 001B. Do you see that? The value of the symbol case 0 is 001B because that's where the code was that's where that code is stored. And look at line 0013. What is that 0013? 001B. Now take a look at case 1 on line 0021. What is the value of the symbol case 1? 0021. So look at line 0015. What's there? 0021. And look at line 0027. That's case 2. What's the value of case 2? 0027. So 027 is there. And then 002D is at 0019. Does everybody see what that is? So that's so now we branch to guess table JT. Okay, so here let's do a computation to see how this works. Suppose the user entered 2. All right? Suppose the user entered 2. So the value of guess is what? 2. So here's an example. So let's do guess equals 2. All right? And we are on line 000C. So we load word index guess, and then that's 2, right? And then ASLX makes what? Makes it what? ASLX makes X equal to 4. Are you with me? All right? And now we branch to guess table JT using indexed addressing. But how does indexed addressing work? The operand specifier is what? You see there on line 0010. What is the operand specifier? 0013. So the operand specifier is 0013. And why is that 0013? Because that is the what? The value of what symbol? Guess JT. So how does indexed addressing work? It adds 4 to this. So remember, so the operand is mem sub what? Operand specifier plus X. So what is this? This is mem sub what? 0013. 0013 plus, and what is in X? 4. So this is mem sub what? 0017. All right, but what is in mem 0017? 00 what? 27. So the operand is what? 0027. So this is a branch to where? 0027, which is what? Case 2. And we didn't have to do any of the else ifs in between. Ooh, I think I broke something. So put that in your pipe and smoke it. Yeah? Does everybody see? So you have a little, I think I gave you a switch exercise problem to do for a future homework assignment. All right? So anyway, this all fits. Once you get this concept of how these memory models work and how these addressing modes work and everything, we're able to do all of this stuff, all these highlighting. Oh, by the way, guess who invented the switch statement? This is a little historical detail. Guess who invented, who first came up with the concept of the switch statement at the hardware level like this and actually did it? You know his name. Dijkstra? No, Dijkstra did a lot, but he didn't do this one. No, Turing? No. He was theoretical. He was too theoretical.
Did he work at like Bell Labs?
I don't think so. I don't think he worked at Bell Labs. Well, who's triple?
Oh.
Yeah, Anthony C.A.R. Hoare invented the switch statement. Pretty clever guy. Yeah, this concept of how to do it. Anyway, a little bit of history trivia. See you next time.